The modern software-defined vehicle projects an image of perfect, calculated safety. Historically, automotive engineering has secured this safety by looking inward, isolating individual hardware components or systematically debugging lines of code to prevent a mechanical or logical break. This inward focus is codified in the ISO26262 standard. It is highly effective at establishing functional safety by preventing physical wear or systematic software faults, but it operates on a critical assumption that the vehicle exists in a closed, predictable environment. To evaluate how systems break, engineers use a concept called the Dependent Failure Initiator, or DFI. In legacy models, a DFI was usually a physical coupling factor, like electromagnetic interference or shared memory corruption. Today, that definition is dangerously narrow. This four-quadrant matrix maps the vulnerabilities of modern autonomous architecture. The extreme interconnectivity of Level 4 autonomy requires layers of data processing that legacy standards cannot secure. In the first quadrant, we have ISO26262, which handles internal hardware and software integrity. The second quadrant introduces ISO/SAE 21434 for cybersecurity. Unlike random internal hardware decay, this domain accounts for malicious external nodes actively exploiting shared vehicle resources and communication channels. The third quadrant addresses the safety of the intended functionality, or SOTIF, under ISO 21448. This maps environmental extremes that can physically blind or paralyze perfectly functioning sensors, even when zero mechanical defects exist. The final quadrant is ISO/PASS 8800, governing AI safety. This targets the inherent risks of non-deterministic black box AI algorithms and the downstream effects of biased training data. We are going to track a single vulnerability as it bypasses each of these specific boundaries. We will follow the failure chain from the external network, through the physical environment, into the AI logic, and finally into the vehicle's structural defenses. Treating these four standards as separate engineering disciplines allows catastrophic dependencies to form. When threats span multiple domains, a siloed architecture enables multi-domain system collapse. Consider a Level 4 autonomous vehicle approaching a busy urban intersection. To optimize its path, the vehicle relies on external vehicle-to-everything, or V2X, signals to read upcoming traffic lights. This split-screen architecture diagram shows how an external attacker exploits a cryptographic vulnerability in the V2X interface. Bypassing a weak software partition, the malicious packet penetrates the vehicle's non-critical infotainment domain. From there, the attacker executes a UDP flooding attack. They inject an aggressive swarm of random data packets directly into the vehicle's high-speed Ethernet backbone, instantly exhausting the network's bandwidth. Look at the right side of the system tree. Deprived of network resources, the CPU usage in the vehicle's critical sensor fusion node abruptly spikes from a stable 30% up to 95% as it struggles to process the noise. This localized CPU spike derails the operating system's processing schedule. Critical sensor ADA frames, which require updates every 50 milliseconds, begin to suffer massive packet loss and severe processing latency. By artificially starving the CPU, the cyber threat defined in ISO 21434 acts as the first dependent failure initiator. It actively induces a classic functional safety timing violation under ISO 26262, eroding the temporal isolation between the vehicle's secure and non-secure systems. As the network stutters, the physical environment deteriorates. A torrential rainstorm hits the intersection at night, introducing worst-case optical conditions to the vehicle's hardware. Headlight glare reflecting off the wet asphalt blinds the camera lens. Simultaneously, the heavy raindrops scatter the near-infrared laser pulses of the LiDAR array, decimating its signal-to-noise ratio. This is a SOTIF common cause failure. Two mechanically perfect, heterogeneous sensors have been simultaneously neutralized by a single external coupling factor, the weather. Now a physical hazard emerges. A large, irregularly shaped flipped trailer completely blocks the intersection directly in the vehicle's path. This scatterplot illustrates the AI's out-of-distribution, or OOD, vulnerability. The dense cluster represents the standard vehicles the AI was trained to recognize. The flipped trailer is an isolated data point sitting entirely outside the AI's training distribution. Starved of processing power by the cyber attack, and fed noisy, degraded data from the weather. The neural network evaluates the irregular radar returns of the trailer and forces the anomaly into a known category. It generates a false positive, clear path signal. The AI has hallucinated. Because the system utilizes a single AI ensemble for both perception and trajectory planning, this hallucination injects a critical logical error into both modules simultaneously. The vehicle's sensor redundancy has failed. An AI dataset bias turned a massive physical obstacle into a phantom, prompting the core processor to instruct the physical actuators to maintain speed. The vehicle has one final line of defense, an ASIL-D runtime monitoring module. Its sole purpose is to audit the AI's output, catch anomalies, and trigger an emergency physical break. But the architecture contains a fatal dependency link. This safety module operates on the exact same hypervisor environment as the compromised AI and networking tasks. This timeline chart maps task execution within the hypervisor. The CPU starvation initiated minutes ago by the Cyber UDP flood continually pushes the safety watchdog task backward. Deprived of compute cycles, it crosses the red timeout limit line before it can execute its checks. The result is a silent failure. The safety mechanism crashes and powers down without ever sending an alert to the rest of the vehicle. This high-speed collision is the direct result of an unmapped dependency chain, one that allowed external domains to bypass every safety barrier and silently assassinate the core safety watchdog. To prevent this specific failure cascade, engineers must move past component-level reliability and build an integrated dependent failure analysis architecture. Every boundary must be physically and logically enforced. We must start by neutralizing the cyber flood. Using standard operating system partitions to separate infotainment from safety leaves critical memory exposed to overflow. This diagram outlines a multi-core system-on-chip layout utilizing a hardware root of trust. A memory protection unit forms a strict spatial firewall, instantly deflecting any malicious traffic attempting to cross into the ASIL-D control memory. Next, to solve CPU starvation, the architecture requires a cache-aware hybrid scheduler. This bar chart models the L3 cache. It dynamically allocates 60% for variable network traffic, but mechanically locks off exactly 40% exclusively for safety tasks, guaranteeing execution time. By enforcing absolute physical and temporal boundaries at the silicon level, the architecture successfully severs the dependency link between an ISO21434 cyber attack and an ISO26262 functional safety system collapse. To defend against the environmental and AI logic failures, engineers cannot rely on symmetric redundancy. Adding more identical sensors or doubling the AI algorithms only gives external coupling factors a larger target for common cause failures. This flowchart details the simplex architecture, built on the doer-checker fallback pattern. It applies intrinsic diversity by separating the logic into two distinct branches, the high-performance doer channel and the high-assurance checker channel. The doer channel runs complex neural networks to optimize trajectory. The checker channel ignores AI entirely. It is a strictly deterministic, rules-based C-code module calculating pure physical kinematics, a mathematical safety envelope based on raw distance and relative velocity. If the doer AI hallucinates a clear path, but the checker module detects that a physical distance threshold has been breached, the checker instantly overrides the AI and forces a hard switch to the fallback braking maneuver. By pitting strict deterministic physics against probabilistic AI, the architecture geometrically traps the AI's dataset bias before it can translate into kinetic danger. Executing a hard setdown when a component fails at highway speeds risks triggering a secondary collision. The system needs a logic of graceful degradation. To preserve critical control, the system initiates load shedding. It deliberately cuts power and network access to non-essential systems like video streaming and telematics, immediately restoring the 5-millisecond control loop required for emergency steering. Using this restored bandwidth, the vehicle drops out of Level 4 autonomy. It executes a minimum risk maneuver, safely decelerating and steering to the shoulder. Modern autonomous safety cannot exist in silos. The physics of the road and the logic of the network are inextricably linked. Building secure, safe automated vehicles requires the rigorous co-engineering of cyber defense, environmental parameters, AI data validation, and functional safety, starting from the very first line of code. The integrated DFA framework thus provides the essential architectural blueprint required to navigate the unpredictable variables of the open road, ensuring that even under multi-domain assault, the system's structural integrity remains intact.